Yeah, thanks. So today we're going to look at how we can analyze and visualize audio in the browser. We're going to focus on speech-based content. So let me give you a little bit of a background before we start. So originally I'm from France. I've been here in LA for about a year. Before that, I used to work in Silicon Valley. And I worked in different industries, work on website, web app, games, a little bit of everything. Work on with different sort of tech. But if there's one tech that I really, really like, it's JavaScript, obviously. Another thing that I like is listening to podcasts. I think it's a great source of learning. And a year and a half ago, I decided to co-found Audio Dive. That's our logo right here in the corner. And so what we try to do pretty much is try to bring a new perspective to the whole experience of listening, discovering, and sharing podcasts. And so we try to take different approach. And so one area that we looked at that really I'm passionate about is visualization. So let's dive in and try to define what it is. So this is a definition from Wikipedia, and it says music visualization, a feature found in electronic music visualizer and media player software, generates animated imagery based on a piece of music. The imagery is usually generated and rendered in real time and in a way synchronized with the music as it's being played. So, all right, that's just word. Let's actually have a look at examples. So we're going to dive back in the 80s. We're going to look at an example of those old school hi-fi systems you see, As a kid, I used to stare at those and just look at those LCD screen. Here's an example. So I don't know why, I just was fascinated by this. And I would try to figure out which instrument corresponds to which bar on the thing. And I just thought it was cool, right? But I was back in the 80s and, the only thing you had to show music visualization was an LCD screen, right? That was the only way. So let's have a look now at a more recent example of visualization. If you grew up in the 90s and you used to listen to MP3, there used to be a software that would do really cool shit, and I love that software. It was, and maybe you know which one I'm talking about, but I'm going to show you a web version of that software. That's kind of all right.
It really whips the lover's ass.
So what I loved about this is that you could just listen to your favorite music and stare at this cool psychedelic. Well, I don't know what came through person's head when we made that, but it looks cool. I'm in, So, all right, let's go back to the talk. So the question is then, can we use a similar technique to then visualize speech in the browser? Considering that podcasts are mostly based off speech, then maybe there's a way we can dig in that direction. So yeah, we work with spoken words. So let's try to define what we need to get there. The first step we need is we need to be able to analyze audio. So we need to be able to read from an input stream or audio, any stream of audio, and then extract the relevant data at a regular interval and as short as possible. So basically, the difference between what you see and what you hear is the same thing. It has to feel the same, right? And then we need to be able to visualize this information, this data we grab, right? And so ideally, we want enough flexibility in the drawing features. And then so that's more a personal preference, but whenever I do something creative, I like to use a library that has a very high level, simple API, so I don't have to spend too much time in the, setting up things, right? Setting things up. So today, I'm going to use a library called p5.js. So p5.js is a JavaScript library that starts with the original goal of processing, which is another library for drawing things, to make coding accessible for artists, designers, educator, and beginner, and reinterprets this for today's web. P5 has add-on libraries that makes it easy to interact with other HTML5 objects, including text, input, video, webcam, and sound. So that's great. There should be enough for us to get started. And we'll see later on why like an example of one of those really high-level API functions that can really help you get forward. So first now have a look at the definition. And the definition is the fast Fourier transform. So a fast Fourier transform is an algorithm that samples a signal over a period of time and divides it into its frequency components. So that's the definition from Wikipedia. And that is pretty much what we need to be able to convert that audio signal into data. So I think the best way to show you how it works is just to show you an example. So let's start a sketch. Sketch is the term we use in P5 to define like a small project. And so what you're looking at here is a spectrum, a frequency spectrum. So when they say that they sample a signal over a period of time, it's a very short audio signal, right? And then they divide into those frequency components. So what you can see on the left side is a low frequency, and on the right bound is more like the high frequency. And so that's pretty much me speaking. So we use the microphone inputs. And so let's have a quick look at the source code so we can understand how we can use those APIs to produce these results. All right, so this is the source code of this example here. And there are actually two functions that you need in P5. There's only really two functions that you need to worry about. First one is the setup function here. And the second one is the draw function. And looking at the setup function is all the initialization, right? So in this case, what I'm doing is that I'm grabbing my microphone input, and I'm using this audio in constructor. And then I'm starting my input. And more important here is that I'm also initializing my FFT instance. And the very important parameter here is the number of bins. In this case, my number of bins is equal to 128. And what it means that I'm going to have 128 bars moving here. Now, let me show you how, let's try to make sense of the data we get from the FFT object. So this function draw is being called pretty much all the time. And behind the scene, it's using a request animation frame. So it's automatically being called by the browser. I'm going to add a small breakpoint here. As you can see, it's already breaking. And so we're going to move one step forward here, right? So as you can see, I have called my FFT instance, and I have called the function called analyze. Behind the scene, it's actually calling the web audio API. There is this thing called the analyzer node that return the frequency data in bytes. So if we look at the data we get from this, we actually get an array of 128 value, which correspond to the number of bins that are passed to my FFT object. And so if we look at the values, for example, here, we have some values that ranges from 0 up to 256, 256, right? And these correspond to the amplitude for that specific frequency component. So in this case, we have for the lowest frequency, which will range in this case from 0 to 344 hertz, we have 234. And as you can see, it's actually this first bar here. So what's great with the P5 is that they have some very useful functions to help you map whatever you get in terms of data to whatever you want to draw on the canvas, right, on your sketch. So if I look at this example here, I'm going to look at this one. So here, what we're doing, for example, we're actually mapping the amplitude of this of each of the bars, so each of the bins, we're looking through them, right? And so what we try to do is to convert this into a bar that can be drawn on that axis here. And what we use here is map. We pass first the amplitude, so let me advance here. All right, so here, for example, we're looking at our first bar. Our amplitude is 234. What map takes as argument is the first range here, from start 1 to stop 1. In this case, it's going to be 0 up to 256, because that's my bound. And then it takes a second range, which is my y-axis, pretty much, right? So by doing that, then I'm getting the correct value, and I can just draw my shape. And in this case, we use the rect, which draw just a simple rectangle. And it's just a matter of then applying whatever we get from those functions into our sketch. So let's keep playing a little bit. Okay, I'm going to remove that breakpoint here. All right. So a thing that we can observe if we look at this is that none of the high frequency sound is actually doing anything here. And that's actually because speech doesn't go as high as those. So it's kind of an observation, but let's try to figure out why. So let's have a look at a little bit of theory behind speech. So according to the CDC website, a person who has hearing within the normal range can hear sounds that have frequencies between 20 and 20,000 hertz. The most important sounds that we hear every day are in the 250 to 6,000 hertz range. So that's kind of cool. It kind of confirms a little bit what we just saw, is that as I was talking, it didn't matter what I was saying. None of those high frequency sounds were doing anything, which means that if I wanted to be able to utilize data, I can just discard all those components, frequency components. And they give you even an example here, for example, like a O sound, like a vowel O, will usually range between 250 to 1,000 hertz. So now that we know this information, can we come back to our example and try to only focus on those range? So in this case, 250 to 6,000 hertz. So when I was talking about P5, one of the awesome function that it provides is this get energy function. And what it does is that instead of worrying about this huge array that I mentioned earlier, you can only get the value that matters to you. And in this case, you just have to specify the high frequency bound and the low one. So basically a range of two frequencies, right? And let's have a quick look at an example so we can try to understand this better. All right, so what you're looking at here is pretty much just the same thing as earlier, except that I only sample data from the 250 hertz range, 250 hertz up to 6,000 hertz. And you can see that it's way more compelling, right? Everything is moving, and it's even moving differently based on whatever word I'm saying, so it's kind of interesting. And if we actually look at the source code here, we can see that would be this one. So what we do is that we first define the number of bars we want to show. In this case, I just set it to 50. And from there, we can divide our range sampling range, and then into those 50 bars. And we get our chunk size, which is like measured in hertz. And then it's just a matter of going through each of those bars, so 50, and simply grabbing the correct get energy, the correct amplitude for the frequencies that we are looking at. So in this specific case, I'm looking at, 250, and then that will go up to 110, so it will be 365. So this is just getting the value from 250 to 365 hertz. And so you do that, and by looping through each of those and using this function get energy, you can then, using the same system, map out only the stuff that you really want. So then the question is, all right, that's cool, but it's just like bars. I mean, there's nothing better than the one we saw earlier on those hi-fi systems. It's just like, all right, so what can we do now that we have this information, right? Well, what I like to do when I don't know what to look at, I just like to browse the web and try to explore examples. So in this case, I just Googled P5 examples, and I came across a nice, very cool example that I'm going to show first here. It's a sketch from, I'll put the credits at the end of the talk, but this sketch pretty much is just a P5 processing P5 sketch that show like a flaring star animated. And so as you can see, let me actually open the actual source code here. As I'm moving my cursor from left to right, the glow is increasing. As I'm moving from up to down, the animation is also changing. So then I realized, okay, that's cool. That's one example. So the code is pretty clean, right? Just like there's a constructor, there is a star constructor. So I assume that I could actually make a lot of those stars, and maybe I could actually try to map one of those frequency components to a star, maybe. And if I know like the right parameter to change in the code, then I can easily transform that thing into something more, lively, so to speak. So let's have a look at an example here. Oh shit, sorry. All right. So as you can see, as I'm talking, each of those stars are actually following exactly my speech. And so what I've done simply is just I've plotted a bunch of stars around. So in this case, I don't remember how many, I think 20, 24 or something. And each of those stars are now following my speech. And it's almost like this kind of organic feel, right? When you look at it, it's like almost mesmerizing, because it doesn't mean anything, but still, it's still based on the actual live input that you get from the microphone. And so then I tried, to push it a bit further, because that's P5, that requires a lot of drawing, but maybe we can try to apply the same example to something we are more familiar with. So like we just talked about the SVG, right? So SVG format, which is great because SVG contains nice drawing. You can have an artist design a nice SVG image, and then it's just a matter of knowing which markups to access. And then you can possibly map those frequency components to shapes that you can see on the screen. So let's have a quick look at another example. And so this one, I just got it from this website, vectz.com. And if you look again at the source code of this SVG file here, what you can see, there's a bunch of paths here. And so each of those, let me actually, all right, yeah, let me close that one. So you can see here, I actually added an ID here, right? So I actually named each of those shapes. I went through the code and then step by step added some ID. and for each of those, and even the little stars in the background. It was quite fastidious to go over each of them, but pretty much it's just a matter of assigning an ID, and then it's just a matter of using a similar technique, and maybe since they all have like a consistent naming, just accessing them. And what I try to do is just use the transform property, Css Transform, which is pretty straightforward to use. So here it is. So as you can see now, each of those planets are moving and, again, following my speech. And it's kind of like funky with those things moving up and down. But it's actually, what's crazy is that it's very simple to do. There's really no rocket science. It's just, in this case, it's called a scale property. So transform CSS property has a scale value, and it ranges. So the default one is 1. In this case, what I've done is simply went from 1 to 1.2, and I mapped that with the amplitude, similar technique that I showed earlier. And yeah, that's pretty much it. So that's just an example to see that it's not that complicated. It's just a matter of plugging things the right way, and then you can come up with some examples like that. So yeah, so that's about it for today. Thanks everyone for watching. If you're interested, you want to learn more about this, you can go to our code pad in here, the code pen, and then you can see those examples as well, the source code and everything. You can follow us on Twitter if you want to know more about what we do. So again, we're in the podcast thing. And yeah, thanks everyone for watching. Thanks js.la for hosting, and thanks Dan and Gian for feedback on this talk. And yeah, if you want to get into creative coding, here are some Twitter accounts that are really good. They're really good at teaching as well, so that could be a good source of inspiration.